Thanks everyone. I am Leandro. I work at Leandro as a two-chain engineer. And today I'm going to talk about optimizations in Flang. And just a quick review about what is Flang. It is the LLVM's Fortran frontend. And it lowers Fortran code to high-level Fortran IR that is then converted to Flang IR and then to other MLIR dialects. From this point on, MLIR and LLVM performs the remaining build steps to produce an executable. So in this slide, we have an example of this step, the lowering from Fortran to HLFIR. And we can see that besides the operations with HLFIR and FIR, there are also some other MLIR dialects being used, such as Funk and Arith. And an important point is that HLFIR preserves many details of Fortran constructs, so it's the ideal stage to perform Fortran-specific optimizations that rely on Fortran knowledge. So before trying to optimize Flang, we need to first evaluate its performance. And for this end, I used Spec CPU 2017, but only the benchmarks that use Fortran. And the tests were run on a new verse V2 machine. And Leonardo's goal is that Flang should be no more than 10% slower than G-Fortran on any benchmark. So by April this year, the latest stable versions of LLVM and GCC were versions 20 and 14. And so in this chart, we have a performance comparison between these two. And we can see that in most benchmarks, Flang performs equal to or better than G-Fortran or with GCC. But in the case of CAN4, it's 18% slower. So CAN4 is a good candidate for optimization. And to identify the functions that accounted for most of the execution time, perf was used on a Ubuntu machine. And I noticed when profiling that the performance issues were spread throughout the program, which made it a bit harder to identify the functions with the biggest differences. So here we have the perf report output, and it's listing the 10 hottest functions of CAN4. And among these, I have selected AR-Red props SW, because if we consider the number of samples, we can see that's almost twice as low when compared to GCC. But when trying to inspect the function, only the assembly instructions were being listed, and there was no debug info. And this was because, unlike GCC, LLVM sometimes loses debug information when LTO is enabled. And a workaround for this is to disable LTO, at least to be able to map assembly instructions to Fortran constructs. So here we have the output with LTO disabled. Now we can see Fortran source alongside the assembly instructions. And AR-Red props is a large function, but something that called my attention was the initialization of three-dimensional arrays. And here we can see that LLVM used several store instructions, while GCC was able to initialize the array using two simple loops. And what it seems that is happening is that LLVM is not realizing that this is initialization of the whole array, and then maybe it could use a single loop to initialize it instead. So when trying to inspect what was the cause of the issue, it's useful to go through each stage of code generation, beginning with HLFIR. That is the first translation from Fortran to an IR. And here we can see that the whole initialization is performed by a single HLFIR operation, that is the assign operation. And when it's converted to FIR, it becomes 3 nested loops that initialize, that stores a double to each array element. That in LLVM-IR becomes a series of get element pointer followed by store double instructions. This was happening because the 2 inner loops were completely unrolled. But since this is a contiguous array, maybe we can use Flang to lower the assign operation to using a single loop. So maybe that could help LLVM to produce a more optimized LLVM-IR. And to do this, we would first need to perform the linearization of multidimensional arrays to be able to then go through it with a single loop. This code has the main parts that perform this optimization. But I'm going to focus on the FIR that is generated when this optimization is applied. As you can see here, the 3 nested loops were replaced by a single loop that now goes over the flattened array, storing the double value for each element. And in LLVM-IR, this also now is a single loop, and it was even able to group the stores of pairs of double this time. And finally, in the assembly instructions, we can also confirm that it becomes only a single loop for the initialization. But unfortunately, in the end, there was practically no difference in the execution time of CAN4. And some possible reasons for this is that AR-read-props SW is a large function, and it spends only a fraction of its time in array initialization. And also, there were other performance issues spread in this function. However, in other test programs, there was a substantial performance improvement, as you can see in the table below. For array sizes between 64 kilobytes and 256 kilobytes, the speed up was about 30%. And another benefit is that the number of instructions needed for the array initialization has been reduced from 38 to 8 in the case of CAN4. And that was my first attempt to optimize CAN4. But after some time, I came back to it to try to optimize it again. At that time, GCC 15 had been released, and I used the main LLVM version instead. And also, at that time, the difference in performance between LLVM and GCC for the AR-read-props function had dropped, thanks to contributions from other Flang developers. So I used flame graphs to help identify the functions that had the biggest differences when comparing GCC and LLVM. And one that was identified was WACCMX-IS. We can see when comparing the two flame graphs that the time spent in the version compiled with LLVM is significantly slower. Zooming into it, we can see that in LLVM, some calls are made to trim and free, while in GCC, it has only a single call to the Fortran compare string runtime function. And this is confirmed by the perf output, where we see that LLVM makes 2 calls to trim, 2 calls to free, and the string comparison is performed inline. And this function is actually quite simple. It's only the string comparison of 2 trimmed strings. But the interesting part here is that GCC was able to simply eliminate these 2 calls. So let's try to see how that was possible. Well, first we need to remember that in Fortran, character strings are padded with blanks to the right. And also, if we check the language, the Fortran language specification, we'll see that in the comparisons, the shorter string operand is always padded with blanks to match the size of the other operand. And what all of this means is that it's safe to drop the trim calls because the relational operator already considers the space, the blanks to the right. So to implement this expression simplification, the first step was to add a new HL3 operation to represent a call to trim. This was because it made it easier to identify the call and also to remove it when possible. And when not possible, this operation was then converted to a runtime call that produces the same behavior of before. And with it, I have written a path to simplify the comparison of characters that can basically be summarized in the following expression, where the comparison of 2 trimmed strings become the comparison of the strings themselves. And here's the core of the code that performs this transformation, but I'm going to skip it and focus on the HL3 before the optimization and after the optimization is applied. It's possible to see that both char trim operations were removed and also the destroy operations were also removed in the optimized version. And the result of this is that CAN4 execution time went down from 217 seconds to 280 seconds. That is an estimated 3.5% speed up. And I would also like to mention that there were many other contributions to Flang performance enhancement from other developers. And this slide lists a few of them, some recent ones. And in this chart, we have the current status of LLVM and GCC. We can see the performance evolution on both. The red columns represent LLVM from 20 to the main version, and the blue columns are the GCC time, GCC 14 and 15. And here we can see that The only benchmark now where Flang performs worse than Fortran is Exchange 2. That is 11% slower when comparing it to Fortran 15. Although CAN4 can still be improved. And in the future, we plan to improve the performance of Exchange 2 and also check how Flang performs on spec CPU V8. And another plans are to test other compiler flags without LTO and targeting the new verse v2 CPU. And also check how Flang with OpenMP performs using spec speed for this. And that was it. Thanks, everyone.
Fantastic. Thank you so much. So we have a few minutes for questions. Any questions? Any questions? Last call for questions. All right. Thank you so much, everyone. Let's give Leandro a round of applause.